My name is Dwight Larson, and I'm an applications engineer in the Cloud and Data Center Power Business Unit at Maxim Integrated. And today I want to give you an introduction to hot swap and power protection ICs and the basic circuits behind those ICs, how they work, why we use them, and why they're important for customers to employ in their power systems. The problem that we're trying to solve with a hot swap IC comes from the fact that we're connecting a de-energized load to an energized backplane or power supply. And when you do that, if you don't have any kind of hot swap or inrush control, when you connect those connectors or plugs, whatever, you're going to get arcing and sparking, for one thing, at the connectors. The second thing is you'll see a voltage spike on the load and on the supply side. You also could have dropout of the upstream supply. You could also have disturbance of other loads. For instance, if that backplane is powering other cards or other load devices at the same time and you plug in a new load device that's not powered, the disturbance of that power supply on the backplane is going to also affect other devices plugged into the system, which affects overall system reliability. You could also overload the power supply due to the inrush to the new load device that's plugged in. And finally, the sudden connection of a load could create electromagnetic and radio frequency interference that could affect other systems. Hot swap devices address these problems because they provide a controlled turn-on of power. They also can detect a failed load. They give you the ability to stagger or delay or time the startup of additional loads. And finally, they give an indication that the power is good, and that allows the load device itself to start working once things are stable and settled. So before I start showing the solutions to hot swap, I'd like to walk through the basic problem. What we have is a power supply that's energized, and then some kind of a removable load device, which has input bypass capacitance and also has some kind of load characteristic, which is shown here just as a resistor, although it could be a current source or a switch mode power supply or any number of things. This switch, which I've shown here, really could be a switch, could be a connector. Typically what we're looking at is two connectors that are mated when a removable assembly is inserted into a backplane or a rack or some kind of modular computing system. When we close this switch, what happens? Well, we have a high current that flows through the switch into the input capacitance of the load. And that high current does two things. First of all, it draws a high transient load on the supply. And second, what we'll see on the load itself, on the supply itself, is that the voltage seen on the load will come up, ring, and then settle out at the final voltage. And this ringing is a problem because we can have very high peaks here. If this is a 12-volt rail, this could be 20 volts, 30 volts, or more. And that ringing is dangerous to the load, it's dangerous to the supply, and it generates radiated noise as well. You get a burst of electromagnetic interference when this happens. So obviously we don't want to have this uncontrolled inrush into the cap, right? Because the capacitor looks like an AC short to the supply, which is not good. So how do we solve this? Well, the first thing we want to do is replace this switch with something else. What do we want? Well, ideally, something like a current source. Because if we have a current source, then we know how much current is being drawn. It can be controlled, and if we have a constant current source here, the output voltage on the load will ramp up smoothly like this. And I'll show why that's true in a second, but basically you'll get a nice controlled rise of the output voltage to its final level, and then there's none of this ringing, and we don't have a big transient on the supply. We don't see the supply drop out, so much better solution. So how do we achieve this? How do we put a current source in series with our supply to the load that we're hot swapping? Well, that's the next step, and I'll show you that circuit as soon as I erase this and redraw it. The way we typically solve the hot swap problem and create something that is a controlled turn-on is by placing a power element, a MOSFET, in series with the supply to the load. Now obviously, I'm not showing it here, but there would still be a switch of some sort, which is the connector. And when we plug in the assembly, that connector plugs in, and then we have a hot swap switch either upstream on the backplane or in the load itself. So you have to kind of imagine that this dotted line could also be over here, right? Okay, when we do this, how do we turn this on in a controlled way? Well, what we want to do is put a capacitor at the gate of the FET, referred to ground, And then we're going to energize that with a current source, a very small current source that'll pull up the gate of that FET slowly. And what that gives us is the typical equation is I equals C dV dt, and that's going to come up a lot in these hot swap equations, or in these hot swap application circuits. In this case, the I is the charging current that we have at the gate of the FET, right? And the C would be the actual capacitance to ground at the gate of the FET. And if we solve this for dV dt, in other words, we say I over C equals dV dt, now we can see that if the current and the capacitor are constant, which they are, we have a constant current source and a constant capacitance, then we get a constant dV dt, which is the voltage slew rate. So what does that give us? Well, we get that same kind of ramp, that nice clean ramp that I talked about earlier, where this is the gate of the FET, it starts from 0 volts, and then it comes up to whatever your rail is, let's say 12 volts, plus the final enhancement voltage for the gate of the FET, which maybe is 5 volts or 10 volts or something like that. So maybe 17 volts of the FET at the end here, depending on the FET type. So this is the voltage at the gate of the FET. Now, the nice thing about MOSFETs is that when we operate them like this, the source follows the gate, basically one threshold voltage behind. So whatever the gate is doing, the source is going to follow that minus 1 VGS sub TH for the threshold voltage of the FET. And the reason that happens is because, if you think about it, the gate is rising, at some point the FET turns on and current begins to flow. And it charges, that current flows from the supply to the output cap and begins to charge up the output. If the voltage at the output rises more than one threshold voltage, in other words, if the voltage at the source of the FET rises to the gate voltage minus the threshold voltage, the FET starts to shut off again. So what we get on the load is a slightly delayed and slightly lower waveform, but it's exactly the same as what we see at the gate of the FET. Now, what this gives us is no voltage gain, but it does give current gain. So we might have a few microamps here at the gate of the FET. We end up with amps flowing through the FET into the load, but in a controlled way. Now, as we mentioned earlier, the charge on the gate is going to be basically a square pulse of current to charge up that cap. And what we get on the load is the same thing, a much larger square pulse of current that comes up and charges the output and brings it up to the final output voltage. So you can see that the two waveforms we're looking at is a steady ramp of the voltage, a square pulse of current. Now, if there is a load current out here, like this resistor, obviously we're going to see a little bit of a resistive characteristic on top of that. And when this thing settles out, it'll come out to whatever the resistive load is. So it won't necessarily go to 0 if there's load being drawn by the card or assembly that was plugged in. So the nice thing about this is that it gives us a very controlled turn on. There's no spiking, no ringing, and we can calculate and figure out what the inrush is going to be. Basically, we can say that the dV/dt of the gate of the FET times the output capacitance gives us the inrush current, the total inrush current to the load. So we'll just draw that up here. I inrush is equal to C dV dt, where this is C out right here. Okay, plus any load current. So we can just say, V out over our load or whatever. And like I say, that may not be a resistive characteristic. It might be a switcher. It might be delayed. It might turn on after the power good or signal goes high. But that is your total inrush current then. So this is really nice to work with because we can control this with our C gate times times the I pull up of the gate. That gives us this dV/dt, which we can control. We know what the C out is because that's a fixed thing, a characteristic of our load device. And then we have a nice handle on the inrush current to the load. So this is your basic N-channel high-side hot swap circuit. Now, there are other ways to do hot swap. three other ways that I'm going to specifically talk about. One is high side P channel, and then of course low side N channel and low side P channel, which is more theoretical, but we'll talk about it.